Hello and welcome back to our next lecture. It is chapter 4. It is all about energy. You have a lot of energy. Do some exercising. 1, 2, 3, 4. 1, 2, 3, 4. Too much energy. Today's chapter, energy.
Welcome back. Good to see you virtually. And we're off to chapter 4 here. So in this chapter, we're going to touch upon energy. I will also revisit a couple of things that we touched upon in that first chapter, kind of previewing a lot of the topics. We'll talk about physical properties and chemical properties. So let's get into it and get going here on chapter 4. First off, as we talked about, properties of matter. A property of matter, for example, is really that sort of characteristic of a substance that you can use really to identify a particular substance. Lots of pure substances have different sort of properties associated with them. For example, water is a colorless solution. It doesn't really have an odor or anything like that. And that's very different than, say, something like ammonia. Ammonia, if you've ever sort of smelled ammonia, like Windex, if you ever use something like a Windex type cleaner, it sort of has that very distinct ammonia smell. Bleach, for example, also has a very distinct sort of smell. And you can use those things to really sort of distinguish between different substances. Now, when we talk about properties, a physical property is a characteristic that can be observed without really changing the identity of a substance. So very common sort of physical properties are things like color, odor. I would say, as we talked about in that sort of early chapter, the state of matter is a very common physical property. Is that thing a solid? Is it a liquid? Is it a gas? Things like melting points and boiling points, also very common physical properties. And that's a little bit different than a chemical property. A chemical property is characterized by really the ability of a substance to either undergo a change or even resist sort of a chemical change that's going to occur. Rust, patina, as we'll talk about, sort of examples of really a chemical change. But usually a chemical change, which is associated with a chemical property, usually will involve a chemical reaction. And we've touched upon it in some previous lectures, but really chemical reactions are oftentimes sort of displayed as chemical equations. And just again, some of the finer points of a chemical equation, we have something, say, like N2 plus, we'll go with H2. Eraser here. Go. H2 making a little NH3. And we'll do a little balancing as we have that law of conservation of mass. So we'll put a 3 there as well. Remember, on the left-hand side of the arrow, as we might have talked about previously, these are what are referred to as reactants. And those, again, are pretty much your starting material. On the right-hand side of the arrow, whatever you may have, in this case, we just have one, but you could have multiple, what are referred to as products. And those are really what are formed as a result of a chemical reaction. So let's talk a little bit more about physical changes and chemical changes. A physical change is a process where the substance is changed, its sort of physical appearance, but really not its chemical composition. So really the hallmark of a physical change is basically what you start with and what you end with are really fundamentally the same thing. It's fundamentally still the same thing. It hasn't really changed into anything else. As our wonderful example here is top ice cream melting on the bottom ice cream cone there. As we know, if we do melt ice cream and let it melt, we will have basically kind of like soupy ice cream, if you will, in the liquid form. But it is still fundamentally the same components that it was in the solid state. You can even get it back by putting it back into the freezer, and it will refreeze into its sort of grand ice cream form. but nothing's really changed. And that's different than a chemical change. That's a process in which a substance undergoes a change in its chemical composition. That basically means what you start with and basically what you end with are fundamentally different. They're not the same thing. So they're fundamentally different. So the two examples here on the previous page, a little bit of rust. Once again, as we might have talked about previously, that's when iron and oxygen actually come together and make iron 3 oxide, and they're fused together. This is patina. Copper sort of goes through oxidation and makes this sort of greenish sort of color. The deal with a chemical change also is you really, in most cases, cannot get back your original sort of starting material by any type of physical means. So you can't freeze it, you can't boil it, whatever it may be to get back those things. So, for example, you can do whatever you want to the rust here. You can put it in the freezer. I guess you can warm it up, but you're really never going to get back the iron like it was and the oxygen like it was by doing any of those sort of processes. Unlike what we have up here with our ice cream cone, which obviously you can put it back in the freezer and you will get back sort of that original ice cream. So physical change, start with, end with, same fundamentally, may just appear different. As we talked about when we make a mixture, those are physical changes. Again, we can find both parts of our component. We can separate out both parts of our mixture, and it's only really a physical change that's happening. Once again, a chemical change, what you start with and what you end with are fundamentally different things, and you can't get back those original guys. So let's take a look at some of these examples here. Which of the following would be a physical change? So take a moment, look through your choices here, and we'll talk about which one should be the right answer. All right, so we got grinding a rock into powder. Sounds very physical to me. It's still a rock, it's just ground up. Hydrogen and oxygen reacting to form water. That's a chemical change. A shovel rusting. So that is obviously the formation of rust, which would be a chemical change. Acid and base reacting. So that's a chemical reaction. Definitely a chemical change. Burning sugar. Again, going to burn and create some new substances. So it does look like to me, hopefully you chose it as well. A should be our correct answer here. Let's take a look at another set. Which of the following is a chemical change? So take a moment and think about each of these options. All right, so if we go through it, melting, that is obviously a physical process, right? As we go from one state to the next, going from solid to liquid. So that's definitely physical. I broke a plate, still a plate, lots of little pieces, but fundamentally still little pieces of a plate all over the place. Hopefully you were careful. Boiling of antifreeze. The key here is boiling. Remember, boiling is like the boiling point. That is a transition from liquid to gas. And that, again, is like a phase change. And that is definitely physical. If we put sugar in tea, we will expect the sugar to dissolve in the tea. That is going to make our friend a mixture, right? And that would be a physical change. I'm going by the process of elimination here. That lighting of a match will be a chemical change. It is, again, when you light a match, you're going to do, if you're doing a traditional match, as you strike it, you are going to do sort of a combustion reaction, kind of similar to like when you light a Bunsen burner. It is going to be a chemical reaction that's going to occur, that's going to create heat and fire. So it should be E here. Let's see. There it is. It is E. All right, so that was a little bit, again, officially about physical changes and chemical changes. Let's then talk a little bit now about energy. And when we talk about energy, a lot of times we talk about several things, and we might have touched upon it earlier as well, but we do talk about the system. And the system is really any part of the universe that we're interested in. Again, It could be your test tube that you're doing the experiment in. It could be a beaker you're doing the experiment in, glass, whatever it may be. And then outside of that is pretty much everything else, which are the surroundings. So when we talk about energy and heat, remember that we have the law of conservation of energy, which means as somebody loses a certain amount of energy, somebody else will gain a certain amount of energy. And there's sort of that perfect transition of energy from one form to the next. So whatever gives off the energy, somebody else will gain the energy. Now, when we're talking about systems, there's really three types of systems that we talk about. And that is an open system. And in an open system, you can have exchange of mass and energy with the surroundings. You could go in and take stuff out. You could also have that exchange of energy. In a closed system, you basically put a stopper, for example, on your beaker or flask. It doesn't allow mass to get out, but energy could still transfer. And in an isolated system, you have no transfer of mass or energy. So here's some examples of that. Here in an open system, you can take out some of the solution. Also, we have the heat and energy transferring. In our closed system, we kind of close it up by putting a stopper on it, for example. That's going to prevent us from removing anything, but we still get the transfer of heat and energy. And lastly, in an isolated system, we're really not getting any transfer that's happening either through mass or the energy. So when we talk about energy, energy is the capacity to do work or to produce change. There's different types of energy that we come across. There's chemical energy, and that is the energy that's stored within the structural units of substances. For example, bonds. When we make or break bonds, those are processes that involve energy. So, for example, if we wanted to actually break a bond, so we have a bond here together and we want to break it, we actually have to put energy in to do that. When they gain energy, they wiggle away from each other. So actually, if we have a bond, that is putting energy in to break that, which, as we also talked about, and we'll talk about more in this chapter as well, we're talking about endothermic process. And if we want to make a bond, we got things moving around a lot. They have to actually lose energy, kind of slow down, allows them to kind of hook in together. And that is going to mean energy is released. When we make a bond, and that is what is referred to as an exothermic process. So when we make bonds and break bonds in a chemical reaction, which, by the way, that is all that is happening in a chemical reaction, is we're making bonds and breaking bonds, and that involves electrons. We are having that transfer of energy that's going to be released. So, for example, if you're holding on to a test tube and that reaction is giving off energy overall, that test tube is going to feel very hot to you. And vice versa, if you're holding onto a test tube and it's sort of a endothermic reaction, you're going to feel really holding on to that test tube. There's potential energy, which is the energy associated with the position of an object, and that can be transformed into kinetic energy, which is the energy of motion. It is the classic example of the big giant boulder tipping on the hill. And obviously it has a certain amount of potential energy up here. When it falls over the hill, it transfers itself to kinetic energy, which is the energy of motion. And then it will basically come to rest. Hopefully nobody's standing underneath our rock that just fell. And it will come to a new potential energy. By the way, the energy that when it hits also transfers to whatever it hits. So, the ground, for example, will pick up some energy as it does that as well. So again, that law of conservation of energy, we don't create nor destroy energy. It is conserved, can be transferred from one form to the next. That brings us up to an idea of chemistry that we talk about in here, but maybe not formally, and you'll talk more about probably in both the next chemistry class and this next one after that as well. And that's the idea of thermodynamics. And thermodynamics is the study of basically the interconversion of heat and other kinds of energy. And there are things that are sometimes referred to as state functions. And state functions is the idea that regardless of how you get there, and energy is an example of a state function, regardless of how you get there, really it doesn't matter. And what I mean by that is there's really kind of only two things that really matter in terms of something like energy. As you can also see there, pressure, volume, and temperature. These are all state functions, is essentially where you start and where you end, kind of your beginning and your ending. So for example, if we look at our hikers here in this picture, they both started here. The red hiker took the scenic route around the mountain. The blue hiker took the more direct route. They both ended up pretty much in the same location. They both have basically the same potential energy, as they both started here and are ended there and started down here. And that is why when we look at things like energy, like calculating the change in energy, that's what the delta means, change in energy. We take the final minus the initial, change in pressure, final pressure minus initial, change in volume, change in temperature, final temperature minus initial temperature. Now, what does this mean? Well, this means, especially for energy, not all reactions, for example, we had a reaction, it was like A plus B goes to E plus F. Not all reactions is a one-step sort of process. It could happen that the first thing that happens is A and B will make C and D. And then maybe C and D will go on and make E and F. And maybe there's a certain amount of energy to do this step, and there's a certain amount of energy to do this step. And if we add these together, and by the way, you could add equations together, kind of thinking of the arrow like an equal sign. Anything that's on opposite sides of the arrow in opposite equations can either reduce or cancel out completely. So it's like subtracting C from C and D from D. And then what happens is everything on the left-hand side of the arrow stays there, and everything on the right-hand side of the arrow stays there. And we'll call this E1 and E2 for each of these steps. And if we wanted to figure out the energy for this process, we would actually just add up each of those steps, and that would give us a total amount of energy. So in a chemical reaction, sometimes people think when they see the overall chemical reaction, it is just a boom, boom type situation. It's a one-way situation. It just completely goes over there. But sometimes it may take multiple individual reactions to get to the overall reaction that you're looking at. There may be some things that are like intermediates that are made as the reaction is progressing, and then those intermediates get used up. So why do we take final minus initial? That's sort of the important part of a state function. And that's why when we calculate things like energy, for example, and certain types of energy, when we look at a chemical reaction, a lot of times what we do is we take our reactants to our products. And remember that our products is really like our final state, and our reactants is our initial state. And a lot of the way that we calculate energy, as we'll talk about here in just a second, is to take really all the energy of the products that we made, and we subtract it from all the energy of the reactants. So that's like our final state minus our initial state. And that's a very common way that we can kind of calculate the energy associated with a reaction. Now, speaking of energy, there are certain units associated with energy. And let's talk about some of these important units here. The SI unit for energy is Newton meters, although most of the time in chemistry, we're not using that. That is also related to what is known as a kilogram times meter squared divided by second squared. But very common unit of energy that we do use a lot are joules. So 1 joule is equal to a kilogram meter squared divided by second squared, which again is a Newton meter. So that is a relationship that does pop up occasionally. Kilojoules is also a very common unit of energy. So joules and kilojoules are very commonly used, and that is our kilo relationship there. 1,000 joules is equal to a kilojoule in this case. Now, traditionally, also chemists will use calories as a unit. And by the way, these are lowercase calories, which is an important distinction here, lowercase c. And that is the amount of heat or energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. And there is a relationship between calories and joules, which is an important one to remember. 1 calorie is equal to 4.184 joules. By the way, we'll see it a little bit later, but there is actually a big calorie with a big C. That is what is sometimes referred to as a nutritional calorie. That's actually equal to 1,000 of the little calories with the little c. And that is also equal to 1 kilocalorie, which is another very common unit of energy. So in terms of energy, I would say the main two are kilojoules and joules, but also calories and kilocalories are also used a lot as well. One way that we use energy is to change the temperature of a substance, like ice to liquid water. Again, energy needs to be absorbed by the ice, and it will cause it to start to melt, as we've talked about before. Now, thermal energy is the energy that is associated with the random motion of atoms and molecules. So thermal energy is really based on the amount of molecules or atoms that are present and basically how much motion you would have. So obviously, the more atoms and molecules you have present, the more vibrations and motion and energy you would have associated with it, and the more thermal energy that you would actually have. Now, there is a difference between thermal energy and temperature. Temperature is sort of a measurement that we use to represent how much energy there is in a certain amount of a substance. But for example, if you have a cup of coffee that is 70 degrees Celsius, it has a higher temperature than, say, a bathtub of water at 40 degrees Celsius. But there is a lot more thermal energy in the bathtub because there is a greater amount of molecules in that bathtub than there is in the coffee, even though the coffee has a higher temperature. So what does that mean? It means if you have this big bathtub full of water, there's a lot of water in there. You have a coffee cup, not so much water, or basically coffee in there. So the amount of energy needed to raise the actual temperature, which is what we look at for water in a bathtub, because there's so much water molecules in there, is a lot more energy to see the temperature change just a little bit. As opposed to in a coffee cup, there's not that much volume, for example, of water, which means you don't need as much energy to change the temperature than you would there in a bathtub of water. So because the water has much more water molecules, or the bathtub of water has much more water molecules present, it will have a higher thermal energy, even though it has a lower temperature. The coffee cup is showing a higher temperature because it doesn't take that much energy to do that. So what would be an example to sort of really visualize this? If you think about if you went and just put in a very small amount of water on your stove, right, in a bowl or something like that, or a pot, I suppose, to boil it, right? You would then put on a pot that is full to the brim with water, and you started to heat it. Odds are this guy over here is going to start to boil faster than this guy over here, because it's going to take less energy because you're starting with a very small amount of water to begin with versus the pot that's completely filled with water. So less energy needed to get it to boil, which means this guy at some point will probably show a higher temperature than the water at that point. If you were boiling them, say, at the same time, you would see that the guy on the left there would be a much higher temperature than the guy on the right. Again, it takes a lot more energy in certain cases to change the temperature of a substance depending on what the substance is. And we'll talk more about that a little bit later on in this chapter when we talk about specific heat capacity. But in terms of thermal energy, it has to do with more how many molecules and atoms are present rather than the actual temperature. Temperature is a measure of solar energy of what's going on. Heat is defined as the flow of energy due to some type of energy difference. And heat always flows from, as we talked about, hot to cold. So the hotter substance gets cooler, the colder substance warms up, and its temperature starts to increase. And there's two types of processes that we've talked about. Exothermic is any process where heat and energy is given off to the surroundings. So when you light a match, you clearly can feel the heat coming off of the match in the fire, and that is an exothermic process. Endothermic process is any process where heat and energy is being absorbed, and that is again an example like our ice cube example. Even if you don't do anything to it, it will pick up the heat and energy from the surroundings and it will start to melt. Again, heat transferring from hot to cold. So if you take an ice cube out of the freezer, it is colder than the surrounding temperature. The surrounding temperature is warmer. So heat flowing into the cold ice cube, causing it to melt. These are energy diagrams, and the guy on the left here is an exothermic reaction, and the guy on the right is an endothermic reaction. We know this by looking at the energy difference. This is our reactants here, and this is our products. So our reactants are higher in energy than our products here. They're actually lower in energy. And whenever you have reactants that are higher in energy, than their products, you can kind of think of it this way. The only way for the reactants to get down there is energy has to be given off. So energy has to be released in this case, and that is an exothermic process. And that's opposite what we see over here, reactants to our products. And again, our reactants are actually lower in energy than our products. And this case, our reactants lower in energy than products on these energy diagrams. That means energy has to be kind of put in here to do so. So these represent a chemical reaction that's happening. When we have a chemical reaction, really the only thing that is happening is we are breaking bonds on our reactant side. And we are making bonds on our product side. So as this reaction takes place, it will climb this hill to the very top of the hill. And we have basically our reactants breaking bonds and starting to make bonds as it climbs the hill. It gets to the very top of this hill. This is what is referred to as the transition state. It is the highest point in energy. And in chemistry, things in high energy are not very stable. Things always are looking to lower their overall energy, and low energy is a more stable situation. So when we get to the transition state, you can see it's really the peak of the energy. And it's really, we have what it's up there, sometimes referred to as the transition state complex. And a transition state complex is this sort of complex where, as you can see there, as it's making its way up the hill, we're breaking bonds and actually making bonds. So you have something that is kind of a substance that has partially broken bonds and partially made bonds. And since it's the highest point in energy, it's not very stable, and it usually will drop down the hill very quickly to make our products in this case. Now, speaking of that hill, there is a hill that the reactants has to climb to get to the other side. And that is what we see here where our reactance energy is, all the way up here. On this guy, it's over here to here is our hill that the reactance has to climb. That is what is referred to as the activation energy. As you can see here, that is the activation energy. And the activation energy it's sometimes abbreviated of E of A, is the minimum amount of energy that's required for a reaction to take place. So the activation energy is really that minimum amount of energy required for a reaction to take place. So really there's kind of two things that are needed for a reaction to take place. You actually need collisions, so you need everybody to hit each other, the molecules that are reacting, but you also need them to hit each other with a certain amount of energy to allow products to be formed. Just so you know, not all collisions when things come together will result in products being formed. They have to actually hit each other in the right sort of orientation, kind of like the active spot. And they also have to have the minimum amount of energy required to do that, which is that hill. As you can see here on our, erase all this stuff so we can see a little bit better, perhaps. As we can see here on our exothermic reaction, our activation energy is just through here. On our endothermic reaction, it is much larger activation energy. And the hill that the reactants has to climb to get to the other side also affects how fast or slow the reaction takes place. So if you have a really big hill to climb, it's going to probably take a lot longer for reactants to get up and over the hill, as opposed to if you had a smaller hill, probably not going to take as long for everybody to get up and over to the other side. So it does affect the rate of a reaction. As we'll talk about in a later chapter, one way that you could kind of speed up a chemical reaction is to add a catalyst. And when you add a catalyst, it will actually speed up a chemical reaction. A catalyst is not a reactant. It's not a product. And it does not get used up in the reaction. It is there simply to facilitate the reaction to happen a lot more efficiently, as a way you could kind of think about it. And by finding this alternative pathway, and a lot of times in a chemical equation, speaking of that, you usually will see the catalyst written on top of the arrow. So maybe it'll be a metal like platinum, maybe it'll say H plus or something like that, which means it's an acid catalyst. But by finding this more efficient pathway for this reaction to take place, what it essentially is able to do is to basically lower the activation energy. So it lowers this hill that the reactants has to climb to get to the other side, if this is the catalyzed reaction. And because the activation energy hill is much lower, it means they actually can get to the other side a lot quicker, and usually that increases the rate of a reaction. Now, here's a couple other sort of diagrams of energy. Again, here, these are our reactants up here, higher in energy than our products. That means the only way for those guys to get down to products is the system has to give off that energy to the surroundings, which means it's exothermic. Opposite here is our reactants going to our products. And again, the only way for it to get up there in terms of energy is it actually has to accept energy into the system, and that's an endothermic process. Now, when we think about exothermic and endothermic in chemical equations and reactions, we oftentimes think of them as either being products or reactants. Exothermic, because heat and energy is being released, it is thought of as being like a product. And you'll sometimes maybe see it written into the equation. And when we talk about an endothermic reaction, it's like it being absorbed or absorbing energy. So it is thought of it as being a reactant. But sometimes, generically speaking, you will see just heat written at the end of the reaction here on product side, and that is exothermic. Or for an endothermic reaction, you may just see heat written again as a reactant. And once again, as you see in these examples, they actually use numbers, which sometimes is done. I would say in most cases, as we'll talk about here in a second, delta H, which is what is referred to as the change in enthalpy. And the change in enthalpy, which is delta H, is a fancy way of saying kind of the heat of the overall reaction. You can actually calculate, we'll talk just a little bit about how to calculate that in a second. But the change in enthalpy is oftentimes used in chemical equations to represent whether or not a reaction is exothermic or endothermic. And if you're given a delta H value and it is negative, that is usually an exothermic type process. If you're given a delta H value and it is a positive number, regardless of the actual number, but the actual value is positive, that is usually a endothermic type process. So in general speaking, when you calculate energy or you have an energy value given to you, if that energy value is negative, that usually implies that that is an exothermic process happening. And if that energy value is positive, it is usually an endothermic process. So as we'll talk about calculating some energy values here in a bit in this chapter, it is really important, especially with energy, not to just ignore the negative sign or positive sign that you may get when you calculate it, because the negative or positive sign basically indicates whether or not that process is exothermic or endothermic. So thing to keep in mind is if you're calculating energy, make sure you keep the negative sign, or if it's positive, it stays positive, because again, that's important in determining whether or not something is exothermic or endothermic. So here we have some equal masses of hot water and cold water in an isolated container, insulated container. Again, heat's going to flow from our hot to cold. As we can see, it will start to warm up as it does that on the cold side, and it'll eventually come to rest at equilibrium between the two temperatures. Basically, the 90 plus the 10 is 100, divided by 2 is about 50 degrees Celsius. Speaking of enthalpy, and we're not going to delve too far into enthalpy, but I did just want to kind of mention a little bit more. The enthalpy is what is sometimes referred to as the change in enthalpy. And once again, that's what the little delta symbol means, is change. Is basically used to represent how much heat and energy is being given off in a chemical reaction. The change in enthalpy is a state function, which means we take our products minus our reactants, which again basically means that we're taking our final state minus our initial state. So as I mentioned before, you can basically add up all the delta H's of your products minus all the delta H's of your reactants. So let's just say, for example, we had 2A plus B goes to 3C. You could actually look up in a table for these values, which is a delta H of F. And you can look this up in a table. And again, obviously I'm making up numbers here, so you won't find these, but you can actually find the right substances. And let's just say A has a value of 50 kilojoules and B has a value of 125 kilojoules and C is negative 286 kilojoules, right? So to calculate the delta H for this reaction, we would take all the delta H's of our products minus all the delta H's of our reactants. We also have to take into account, if we were to do this calculation, we do have to take into account the coefficients in the equation. So there's 2, 1, and 3. So what we would do is, if we were calculating this in this made up one, the delta H of this reaction would be our product. So we're going to take the coefficient, which is 3, times the value we find in that table, which is minus 286 kilojoules. That takes care of all of our products. We'll do the same thing for our reactants. So the coefficient is 2 for A. We'll go look up A's value, which is 50. We will then add it to the coefficient for B is 1 times the value of B, which is 125 kilojoules. And that takes care of all of our reactants. So once again, our products minus our reactants here. So final state minus initial state. So if we did this here, grab my calculator, we would take 3 times negative 286 minus 2 times 50 plus 125 times 1. And we would get a delta H for this reaction of minus 1083 kilojoules. So what this number would tell us in this case is, didn't write that too straight, but we have a negative value. So overall, this reaction would be exothermic. So that is the way you could calculate delta H. We're not going to probably do much of that at all. You'll do more of that when you take the next class, but that is how you could calculate the delta H for a reaction. You add up all the energy of the products, you subtract it from all the energy of the reactants. And that's what we see here. The delta H is, in this particular case, this is our reactants to our products. And if you just think about it here, we take our products minus our reactants. Our products is a smaller number minus a larger number, and that's going to give us a negative value. And if we look here again, our reactants is lower in energy, which means it's a smaller number than our products in terms of energy. So in this case, we would take our products, which is a larger number, minus a smaller number, and that's going to give us a positive number, which is endothermic. So let's talk a little bit more about energy here, and one way that we can measure energy, and that is what is known as specific heat capacity. Specific heat capacity is the amount of energy that's required to change the temperature of 1 gram of a substance by 1 degree Celsius. That's a very similar sort of definition to calories, which is the energy required to change 1 gram of water by 1 degree Celsius. There is a specific heat equation, which is Q is equal to ms delta T. And in this case, Q is our heat, our energy, and it has units typically of joules or calories. S is the specific heat capacity, and this has units of joules per gram per degree Celsius or calories per gram per degree Celsius. That is the definition of specific heat capacity, the amount of energy required to raise 1 gram of a substance by 1 degree Celsius is basically what it is. M is mass, which is in grams. And our change in temperature should always be final temperature minus initial temperature. And this is one of the few things in chemistry that you actually can leave in degrees Celsius. Now, I will say some books and some people will use some different symbols for specific heat capacity. I personally use the S most of the time for it. Some books, including I believe yours, will use the C for it, specific heat capacity. And I've even seen some books use SH for it as well. So I believe your book will use C. I personally use S a lot, and so they're basically the same thing. There's some different symbols that are used for it. Now, the specific heat capacity of liquid water is a very good number that you should know. So the specific heat capacity for liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That, as you might remember, is also the conversion to go from calories to joules. By the way, specific heat capacity does change depending on the substance's state. So liquid water specific heat capacity is different than, say, ice. Ice is more like 2 joules per gram per degree Celsius. So it's very important to make sure that you do look up the value there. And here is a table from your book of some of those values. Once again, this is the one you probably should know. But as you can see here, ice 2.06 rather than 4.184. So why is it important, for example, when we look at this equation, to make sure that we do our final temperature minus our initial temperature here? It is because that is what's going to determine the sign that we end up with for Q. Mass is going to be a positive number. Specific heat capacity will be a positive number. So the only place where negative number or a positive number can happen is with the change in temperature. And that's important because if you calculate Q and it is a negative value, that would imply that this is going to be a exothermic process. Heat and energy will be released. If you calculate Q and it ends up being a positive number, kind of like our enthalpy, it will be a endothermic process. So it's really important to always do final minus initial. Sometimes people are taught, just take the difference. It doesn't really matter. It does matter. You want to always take final minus initial because that's really where you're either going to get a negative number or not get a negative number. So always do final minus initial for your change in temperature. All right, so let's take a looky here at an example. So why don't you take a moment here and determine the amount of energy as heat that's required to raise 10 grams of a sample of aluminum that has a specific heat capacity of 0.89 joules per gram per degree Celsius from 25 to 58 degrees Celsius. Give the answer both in joules and calories. So why don't you take a moment and see what you come up with? Okay, so obviously we're doing specific heat capacity, so we probably want to start with our formula. Q is equal to ms delta T, or again, mc delta T. We label our stuff here. We obviously have the mass, which is 10 grams. We have the specific heat capacity, which is 0.89 joules per gram per degree Celsius. We have an initial temperature of 25 degrees Celsius and a final temperature here of 58 degrees Celsius. So we're good just to plug it in here. Q is going to be our 10 grams. Our specific heat capacity, 0.89 joules per gram per degree Celsius. Once again, final temperature minus initial, so 58 minus 25 degrees Celsius. All right, so if we do this here, grab the handy dandy calculator, 58 minus 25 times 0.89 times a 10, going to give us, go down here, about 293.7. The units here, Celsius will cancel, grams will cancel, joules. Significant figure wise, I got 3 sig figs there. I got 2 sig figs there. Truthfully, I got about 33 there, which means that's about 2 sig figs, which means probably should end up somewhere like 290 joules. Our Q value here is positive, which makes sense because this is a endothermic process. That means heat is being absorbed. And how do we know that? Well, we actually see the temperature rise, right? So it is picking up heat and energy, and that means that its temperature is going to reflect that it is going up. By the way, we also want to convert this into calories. So a reminder that there are 4.184 joules per 1 calorie. And we take 290 divided by 4.1884. That's going to give us about 69 calories in this case. Now, speaking of specific heat capacity, since we're not too far from that, so let's just go back there real quick. What does it mean when we have a large value for our specific heat capacity, joules per gram per degree Celsius, basically? Well, it means that it would actually take a lot more energy to move 1 gram of that substance by 1 degree Celsius. So if I took something like water, which has a relatively high 4.184 joules per gram per degree Celsius, versus something like lead, 0.128 joules per gram per degree Celsius. If I had the same amount of each of those substances, it would take a lot more energy to see the temperature of the water change by 1 degree Celsius than it would to see lead change. So it has to put less energy in there to see a bigger temperature change for lead versus something like the liquid water. So again, going back to that idea of the bathtub with all those water molecules versus the cup of water, hot water, there's a lot more water molecules in that bathtub. It will take a lot more energy to see the temperature go up by 1 degree Celsius than it would in that small cup of water that has a lot less water molecules in it. So you could take a little bit more energy, and because there's less mass in there, it's going to actually show a much higher temperature than the guy where the bathtub has a lot more mass. This is also why people get a little concerned when the water in the ocean goes up by a very small amount of temperature. Sometimes you hear those reports and go, that doesn't seem like a lot of raise in the water temperature. But if you think about how much water there is in the ocean, that is a tremendous amount of energy just to get that temperature to budge that little bit of temperature scale to go up. So that's why people are concerned about that, obviously, because even though it may seem like, oh, it's a very small change in the overall temperature of the ocean water, but it takes an enormous amount of energy just to do that little bit of change because water has a very high specific heat capacity. All right, let's take a look at another example here. 294 joules of energy is transferred to 10-gram sample of silver at 25 degrees. What will be the final temperature of the silver? The specific heat capacity of silver is 0.24 joules per gram per degree Celsius. So why don't you give that a go and see what you come up with? Okay, so let's take a look here and see what we got going on. So once again, we're using our specific heat equation. Now, in this case, we actually have Q given to us. And remember that Q is, make that 4. Add 4, give the eraser out. 4 joules. So remember, Q actually only has 1 unit. Specific heat capacity, which is right above there, has the 3 units. So sometimes people will get kind of this guy and this guy confused and backwards. So make sure you're conscious of that. The mass here is going to be 10 grams, and our initial temperature here going to be 25 degrees Celsius. So really in this case, we have everything except for the change in temperature. So we can actually put it in. Our change in temperature, we're going to take these guys and divide it to the other side, would be equal to Q divided by MS. Putting in our values there, that's going to be 294 joules divided by 10 grams, and our specific heat capacity of 0.24 joules per gram per degree Celsius. Joules are going to cancel, grams are going to cancel, Celsius will come to the top when we divide it. That's going to give us a 294 divided by 10 divided by 0.24. That will give us something like 122.5 degrees Celsius. Remember, though, that is not the answer. That's actually just the change in temperature. So the change in temperature is our final temperature minus our initial temperature. So we got a 122.5 degrees Celsius equals the final temperature, which is what we're looking for, minus our initial temperature. So we're going to add that to the other side. That will get us roughly a final temperature here of about 147.5 degrees Celsius. If we want to sort of follow along with significant figures, really at the end of this procedure, we had two significant figures, which technically would take us to here. And that means that basically we're taking a whole number, right? That technically would round to 120 plus our 25. So we can take this down now at the end to maybe a whole number of 148 degrees Celsius. Again, if you rounded earlier and did the 120 plus the 25, you would end up at 145. Either way would be fine. Again, personally, I probably wouldn't round at this point since I know I'm kind of going to do one more step, and I would round here towards the end. So what we want to talk about now that we talked a little bit about specific heat is the idea of how heat transfers in this situation. So let's say we had a beaker of water. And let's just say that the initial temperature of this water was 28 degrees Celsius. And let's just say we had 125 grams of it. And we know, obviously, the specific heat capacity for liquid water is 4.184 grams per degree Celsius. Let's say we took a piece of metal here and we heated this metal up to an initial temperature of 98 degrees Celsius. And let's just say we had 25 grams of this metal. And let's say that we are looking for the specific heat capacity of this metal. So we take this metal and we throw it in to go for a swim into my water. Now, the metal is at 98 degrees. The water was at 28 degrees. We would expect now the metal to transfer that heat and energy to the water as it's warmer, right? Heat going from hot to cold. So maybe that warms up our water to a final temperature of 31 degrees Celsius. So if we want to know what the specific heat capacity is, we could actually do some calculations. By the way, once my metal goes into my water and it sits there and it releases all that energy, what will be the final temperature of the metal? It will actually be the same as the water. They'll come to become equilibrium with each other, and we'll end up with 31 degrees Celsius. So if we think about what is happening in this case, we have everything that we would need to know for the water here. We have the mass, which in this case was 125 grams. We know the specific heat capacity of the water, which is 4.184 joules per gram per degree Celsius. And we know that the final temperature was 31 degrees minus our initial, which was 28 degrees Celsius. So if we do all that there, we take 31 minus 28, we'll times it by 4.184 and times it by 125. That'll get us something like 1,569 joules of energy. I'll gonna take it here to maybe put some decimals on this here so we're not rounding so much on each of these. So we'll do put some zeros on there. So when we do the subtraction here, this would technically be 31.0 minus 28.0. So we'll kind of get rid of that for a second. And that would get us basically a difference of 3.0. And that will be 2 significant figures here, along with our 4 significant figures and our 3 significant figures, which means we will go to here and we'll end up with something like 1600 joules. So I kind of fixed that there so we didn't go so far into a 1 significant figure. In this case, we see that this value is positive. It is endothermic for the water. And that does make sense based on our picture. The water is the one basically receiving or absorbing all that energy. Now, how does that help us with the metal? Well, all the energy that the water picked up had to come from one source, and all that was from the metal. So all of that energy that the water picked up came from the metal. So there is a relationship in this type of situation where Q of the metal will equal minus Q of the water. And that means that the Q of the metal in this case will actually be negative 1600 joules. So it's the exact same amount of energy was lost by the metal, and that is why it's negative in this case. Then it was absorbed by the water, which was positive in that case. That is the law of conservation of energy, right? No energy is lost, so all of it is completely transferred from the metal to the water in this case. So how does that help us with our metal? If we think about our Q of our metal, we now have everything that we need. We have the metal, we have the change in temperature, and we have the mass. We could solve for S. We're going to take the M and the delta T and divide them both to the other side. And that will give us Q of the metal divided by M delta T. So when we put our numbers in here, this would be minus 1600 joules divided by the mass of our metal, which was 25 grams. Now, also really important when we do the change in temperature. The final temperature of our metal, because it cooled down, was 31.0. Our initial temperature of our metal, which was hotter before it went for a swim, was 98.0 degrees Celsius. That's really important because this right here is going to give us a negative value that goes with the negative sign that we have here, which will turn our specific heat capacity into a positive number, which is what it should be. So let's punch that in. 1600 divided by 25 divided by 31 minus 98. Going to give us a specific heat capacity here of 0.96. The units do not cancel. Joules per gram per degree Celsius. Joules per gram per degree Celsius. So this is a very common way to figure out how much energy is being absorbed by the water, or even in a chemical reaction, you could do this type of experiment where you simply use 2 coffee cups. They're very insulated. You do the reaction in the coffee cup, and frankly, all you need is a thermometer. And you can use a thermometer to watch the difference in the water. Because most aqueous solutions are water-based, you can basically use a specific heat of water, and you can basically figure out, based on how much energy the water gains, or even how much energy the water loses, you can then relate it back to something else like the metal, or how much energy is happening in that reaction. So the relationship that we just looked at here is really this relationship here. The heat loss should be 0, and that would be the amount of the water specific heat plus the specific heat of our metal, basically. And since they're both on one side, they're equal to 0, you basically have to move one of these things to the other side, and that's where the negative comes from. So this is really the long way of doing what we just saw there, that the Q of the water is equal to minus Q of the metal, or vice versa, however you want to do it that way. Get rid of, I think I wrote it the other way, so we'll do it that way. So that's sort of the long way of doing that relationship. So somewhere along the way, you got to change the sign so that you get everything correct. So why don't you try one here? That's sort of the same situation as we just talked about. 110 gram sample of a metal at 55.5 degrees Celsius raises temperature of 150 milliliters of water from 23 to 25.5. Determine the specific heat capacity of the metal in joules per gram per degree Celsius. So why don't you take a moment and see what you come up with. Okay, so let's take a look. This is sort of the same idea. We basically got some water and we got a metal. Got some water. So we could kind of list both of these things separately. We have our metal information and we have our water information. So let's take a look at each of these. For our metal, we have the mass is 110 grams. We have an initial temperature of 55.5 degrees Celsius. Raises the temperature of water, which is a volume here of 150 milliliters. It moves from an initial temperature of 23 to a final temperature of 25.5. Remember, since it is liquid water, we also always have the specific heat capacity of it, which is our number here. What we also know from our conversation is when we drop this in here, this guy started at 55 degrees, basically, and the water was 25 degrees or so. That means that the metal is going to be hotter than the water, which means it's going to release this energy. And once it goes for a swim, it eventually will end up at the same temperature as the water, which means we now know for our metal, the final temperature, which is going to be 25.5 degrees Celsius. We are looking for the specific heat capacity. That means somewhere along the way, we will also need to figure out the Q. So just like previously, we could really focus on the water part first, since we know all the information for the water, and we can put it into our specific heat equation. So let's do that for the water here. Our Q of the water will equal the mass of the water. And we do not have mass here, but we do have volume. Remember that the density of liquid water when you need to use it in a problem is 1 gram per milliliter, which means if I multiply this by the density, right, because density is mass divided by volume, which means mass is volume times density, right? And that's essentially what I'm doing here. That will give me 150 grams of water. So now I have this in the correct units for the water. Our specific heat capacity of our water, which is our liquid water. And again, our final temperature, which is 25.5 minus 23.0 degrees Celsius. So taking our calculator here and doing this, times 4.184 times 150. Again, here going to get us about 1,569 joules. Celsius will cancel, grams will cancel, leaves us with joules as our answer. Significant figure-wise, we got about 2 sig figs there. Again, we got 4 here and 4 here, which means really this should be, again, about 1,600 joules if we kind of clean it up. Now that we have the amount of energy that was picked up by the water, remember that all of that energy had to originate from the metal. So we know that the Q of the water is equal to Q of the metal. We just need to change the sign. So now that we did that calculation, we know that for the metal, it should be minus 1600 joules. Again, it's going to be exothermic for the metal as it's releasing that energy to the water. And now for the metal, if we're ready to do our calculation, we should have everything that we need. So our Q of the metal will equal ms delta T. Solving for S means we're going to divide both of these guys to the other side, and that will give us S of the metal is equal to Q of the metal divided by M and delta T. Putting in our numbers, minus 1600 joules. I feel like I put an extra decimal in there. That shouldn't be. Let's try that again. Minus 1600 joules divided by our mass, which is 110 grams. Once again, we want to go final temperature minus initial. That's important for the sign here. So that's going to give us 25.5 minus 55.5 degrees Celsius. And if we do that, that's going to give us 1600 divided by 110 divided by 25.5 minus 55.5. Going to give us, we'll call it 0.48 on my calculator. Again, the units do not cancel, so that is joules on top, grams and degrees Celsius on the bottom, joules per gram degrees Celsius. So again, a very common approach used in a lot of experiments to figure out how much energy is happening in a reaction. Very simple sort of process. You actually just need a thermometer and you can pretty much figure out a lot of what's happening in terms of energy of chemical reactions. So let's talk a little about energy and nutrition. As I mentioned before, when we talk about calories with a capital C, that's a nutritional calorie, and that is 1,000 of the little calories or 1 kilocalorie. A calorimeter is an apparatus that's used to determine the number of calories in food, for example. This is what is sometimes referred to as a bomb calorimeter. You basically have a very well insulated container. You have water, you got a thermometer in there. You have some oxygen and some ignition wires. You put your food sample, like your cookie, down there on the sheet. You ignite it. It catches on fire, basically. All that heat gets transferred to our water. And really just doing a very simple calculation like we just did, they could figure out how much energy was absorbed by the water. And in turn, they can figure out how much energy was released by, say, your chocolate chip cookie. And the result of that is they could then convert that into, say, regular calories to nutritional calories and figure out how much calories are associated with your food item. They used to do at this school years ago. They might still do it. I don't remember, but we used to years ago. You could take like a soda can and fill it with water. You take like a food item like a Cheeto or something like that. And basically you would set it on fire underneath and burn it. As the food is burning, it will obviously heat up the water in the can. And again, just by simply following the change in temperature of that water, you can figure out how much energy is being absorbed by the water. And that obviously is all the energy is coming from your food item that you're burning. So that's sort of a very similar sort of idea. Now, when we talk about caloric value for food, there's 3 types of food that we deal with, which are carbohydrates, fats, and proteins. And that's really where all of our calories of our food sort of come from. And one way that we could do that is the kilocalories for, got a little bit moved around for each of these here, but basically the kilocalories for carbs is 4 kilocalories per gram. For protein, it also is 4 kilocalories per gram. And for fat, it is 9 kilocalories per gram. So essentially, when you look on the back of like a food package that has a nutritional label, there's usually a section where it lists carbs and it'll tell you like the total grams of it. There's usually a section that tells you how much protein's in there, and usually a section tells you how much fat is in there. And usually there's a section that tells you how many calories there are per serving. When you find all those values, you basically can multiply those guys by the caloric value of each of these, and then you can basically figure out how much calories there are. So for example, if we had something like that, so let's take a look at one. I think I have it out of order. We'll come back to that there in just a second. So if we take a look at an example of this, we had 28 gram serving of oat bran cereal with some milk. It gave us basically 22 grams of carbohydrates, 7 grams of fat, and 10 grams of protein. If I ate 2 servings of it, how many kilocalories or nutritional calories would that be? So really, we're just going to add up everything. So that is how many grams of carbohydrates there were times the caloric value for carbohydrates gives us basically 88 calories of carbs. If we do that for our fat, 7 times the nutritional value or caloric value for fat gives us about 63 kilocalories, and protein here, about 10 grams in this example, is 40. If we add that all together, that basically gives us 191 kilocalories, which are nutritional calories per serving. And since I ate 2 servings, I basically would have ate about 382 calories. I would say if you do the math yourself on some of the nutrition labels that you find, maybe you're looking at your candy bar or whatever it may be, I find that typically they round down for some odd reason. I imagine why they'd probably do that. They actually round down a lot of times for your calories. So probably something like this would probably be 190 calories or something like that. But that is how you get to those values that you see on those nutritional labels. To finish up sort of talking about experiments involving energy here, as I mentioned and alluded to, we can do these type of calorimetry type of experiments very simply by taking 2 styrofoam coffee cups. It's a very simple process. It's used a lot. You could do it for, like we were talking about, tossing, for example, a hot piece of metal into water, figuring out how much energy was lost by the metal and gained by the water. You could also do just regular chemical reactions, mix 2 solutions together and let the chemical reaction occur. And in these styrofoam cups, they're very well insulated, and you have a thermometer, and you can put a lid on it to make sure no energy basically goes through it. And by just simply following the change in that water and using our specific heat equation, we again can figure out really how much heat or energy is being gained or absorbed as a result of a reaction. Now, when you do this at constant pressure and you actually do this type of experiment, when you calculate Q, which is our heat, it will essentially be the same as the change in enthalpy for that particular reaction under constant pressure conditions. So if you wanted to calculate the change in enthalpy of a particular reaction, and you'll do this probably in Chem your next semester, and you might do it here as well, but definitely in the next semester you'll do it. You'll grab a couple of coffee cups, and you just pour things in there and let it do its reaction by just simply following that temperature change and using your specific heat equation. You could actually do a little bit of a conversion and relate it to the enthalpy of that reaction. Once again, take home message here for energy. The sign is really important. Anything that is a negative value for Q or delta H is an exothermic process. That means heat and energy is being released. Anything that is a positive value for Q or a positive value for delta H means heat and energy is being absorbed. All right, I believe that should wrap up actually chapter 4, I think we are on here today. So that should do it there. So we will end the recording here for this one. Thanks for watching. Have a good day, and I'll see you again on the next chapter. Bye-bye.
Hello there, and welcome back. It is time for a chemistry joke. How often should you tell a chemistry joke? Periodically.